Hello and welcome back to Physics for the 21st Century. Again, my name is Greg Perugini, and today's topic is angular momentum. We already covered linear momentum, momentum in a straight line. If you remember, P equal mv. And you remember that we have some linear equivalence rotationally. We talked about, of course, force is equal to ma, then therefore torque is equal to, rotationally we have to take into account the geometry, alpha being rads per second squared. Momentum is a vector, of course, so is velocity. Mass is a scalar. So if we have this type of equivalency going on from linear to rotational, what is the equivalency, do you think, from linear to rotational now in terms of momentum? We're going to use L for momentum. I, again, we have to take into account its geometry. Omega, rads per second. Now, just like torque is equal to force times the radial arm, momentum is also thought of as angular momentum is equal to regular momentum times the radial arm. Linear momentum times the radial arm. I can break that P into mv, of course, and then you have L equal mvr. But to know that it's conserved is the key point here. All other things being equal, just like with momentum, if I don't have a non-conservative force acting, or non-conservative action taking place, such as friction, momentum is conserved. So given that conservation, if you look at that I omega initial equal I omega final, you can look at that and say, okay, if it's conserved, if I know the geometry and I know the initial speed, if I change this geometry, then the speed is going to change up or down, right, to keep the equality. That angular velocity will change if the shape or geometry is changed. If the radius gets smaller or the mass gets less for some other reason, whatever it might be. The changes can occur by a flattening of a disc, an ice skater pulling in her arms, changes her I, her moment of inertia. A bar is shortened. Velocity can change for kinematic reasons, whatever it might be. Mass can also be increased or decreased. Let's just do an example of this. Okay. So I'm going to start with a sphere. Okay. Let's start with a sphere. It actually has two levels to it, but all the way to the outside is 0.4 in radius from the center. It's 5 kilograms. So you could think of this as like a tire. And it's going at 1,000 RPM. So tell me, what is its angular momentum? since we know it to be I omega, I'm looking at this disk and trying to figure out my variables. What do I got? Well, the first thing is this. I know for a disk, one half mr squared relates to geometry in an angular fashion, equivalency to mass, linear. So that is 1/2 times 5 kilograms times 0.4 squared gives me 0.4. Omega, well, we have 1,000 RPM, so let's just write 1,000 revs for every 60 seconds. And of course, 2 pi rad, like we've done several times before, is 1 revolution. So that's about 104.72 rads per second. So given those two, angular momentum therefore is 0.4 times 104.72. 41.89 kilogram meters squared per second. The angular momentum. Now, if you remember in our previous topics, we did kinetic energy, and of course, kinetic energy, 1/2 I omega squared, right? The equivalent in terms of linear motion, of course, is 1/2 mv squared. So I could easily figure out the joules involved in this rotation. But let's now take a look at something happening to this disk and work with conservation of angular momentum. Let's say this outer layer falls off. Goes off. We know angular momentum is conserved, so we have that 41.89, but we've lost 1 kilogram and we lost the radius. The radius is now 0.3. So what happens? We have a new moment of inertia, but the angular momentum is conserved. So obviously it's going to affect, like we said before, the rads per second. Let's see how it affects it. So now our I is equal to 1/2 times the new mass, 4 kilograms, times 0.3, the new radius squared. That's equal to 0.18. Drastically reduced. And so now we know that whatever L is equal to, whatever omega is equal to, it must multiply by moment of inertia, give me that 41.89. Therefore, if we call that omega final, this being linear angular momentum initial and angular momentum final, and it's conserved. So what happened at the beginning, whatever the angular momentum was in the beginning must equal the angular momentum at the end. Obviously, our speed is going to change. Our speed is going to increase. So if you take 41.89 and divide it by 0.18, I'm going to get something like 233 rads per second. Okay. Notice that we went up quite a bit from 104 to 233. If we look at this in terms of RPM, of course, we could say 233 rads per second and multiply that by 1 revolution is equal to 2 pi rad, and multiply that by 60 seconds is equal to 1 minute. That will convert back to RPM. The equivalent RPM, if you do that math, is about 2,224 RPM. RPM speeds up drastically. Okay. Well, we could also look at just something like a rotating sphere. If we talk about a rotating sphere, say the Earth. Now, if we rotate the Earth, we know it's omega, right? It's 2 pi rad for every 1 revolution. Does 1 revolution, of course, every 24 hours. And 1 hour is equal to 3,600 seconds. So as you can see here, the hours cancel, the revs cancel, and I'm still left with rads per second, which is the omega, just something like 7.3 times 10 to the negative 5th rads per second. Now, a radius in terms of I is, a sphere in terms of I is 2/5 m radius squared. So, the I value that we'll be dealing with is 2/5 times what is the mass of the Earth? 5.972 times 10 to the 24 kilograms. What is the radius of the Earth? 6.37 approximately times 10 to the 6th. Have to square it. That gives me something like 9.7 roughly times 10 to the 37. That is my moment of inertia. Kilogram meters per second, moment of inertia, right? But now, let's get the angular momentum, which is equal to moment of inertia times rads per second, the angular speed, which is equal to 9.7 times 10 to the 37 times our speed, 7.3 times 10 to the negative 5. That's going to give us roughly, if you do the calculations, kilogram meters squared per second. So, if something would happen to the Earth where it would lose a lot of mass all of a sudden, I don't know what that would be, or it would gain a lot of mass by being struck by something, obviously it's going to change our rotation because angular momentum is conserved. Okay, so in conclusion, remember that momentum is conserved. The before must equal the after. Make sure you have your conservation of inertia, conservation of momentum and conservation of inertia in terms of moment of inertia. Have those geometries ready for you when you take your assessment. And review kinematics and conversions. You may have to convert like I did here. Or if given rads per second initially and then taken to rads per second final, obviously you have rotational kinematics concerning getting the alpha rads per second squared. So there you have it, angular momentum. And good luck.